perhaps the simplest arithmetic operation is addition. So I'll start with that, and I'll specifically talk about how we can build binary adders. But before I get started with this, I want to review a little bit about how we can add a couple of binary numbers. And the procedure is really simple, but I'm covering it here because I'll be referring to it when I'm building the different circuit elements that will perform the same exact procedure. So let's get started. So what I have in here is I have a couple of numbers that I'm trying to add, which are 14 in decimal, and that's what this means in here, and 10 in decimal. So of course 14 plus 10 is 24. What I did here is I converted it to binary so that I show you how you can add a couple of numbers in binary. This is kind of like a second grade, but in binary number. So let's talk about it here. So what I have is I have a 0 plus 0. Well, I know that 0 plus 0 is 0, and the carry to the next bit is actually 0. And then I can think about it as 0 plus 1 plus 1. It's technically, if you think about it in terms of decimal, it's 2, okay? But we know 2 in binary is just 0, 1. So what I'm going to do is I'm going to say, well, it's 0 and the carry is 1 to the next bit. And the same procedure goes on here. So what we have is 1 plus 1 plus 0, which is the same exact answer, 0 and 1. And here, the last one, I have 1 and 1 and 1, which is technically in decimal, it's 3, but I know in binary 3 is 1, 1. So technically it's just 1, and I have a carry out in here as 1. And I'm calling it carry out because usually when we deal with these binary additions, we say, well, I have 4-bit and 4-bit, so the answer is 4-bit, and I might have a carry out to the next circuit or the next bit or whatnot. Anyway, the procedure is pretty straightforward, and we will build a circuit that will implement this particular procedure. So let's get started. So I will start by building what we call a half adder. So what does a half adder do? Well, it does exactly that process of taking a bit and another bit, and then it gives me the answer and maybe a carry to the next step. Well, it always will give me a carry. So if you take a look at its just block diagram in here, or the graphical symbol in here, it's actually a box that takes a couple of inputs, and these inputs are just 2 bits, 1 bit here and 1 bit here, that's similar to 0, 0, and it will give me the sum and maybe a carry. So that is actually shown in here in the truth table. So this truth table, I encourage you to pause a little bit and see that it's actually doing exactly what we expect it to do. For example, in here 0 and 1 is just, the sum is 1 and the carry is 0. Okay, so take a pause and just take a look at that. So after you pause, you'll see that, and take a look at the truth table, you'll see the implementation is pretty straightforward. It's just the sum is one function and the carry is a different function. It's just a basic combinational circuit, and we can implement it using that. So a half adder, which is the very first step of doing these two additions or to add two binary numbers, is pretty straightforward. It's a couple of gates. So let's go to Vivado or Verilog and see how we can actually implement this. Okay, so now we're in Vivado, and I have opened a new module, and I called it a half adder. So what I have to do is I just have to implement this particular black box here. And as usual, what I would do is usually start with the inputs and outputs. And what I do have is I have a couple of inputs, which are X and Y. And I also have a couple of outputs, which are just the carry and the sum. Okay, so that's good. That's pretty straightforward. Now, how do I implement the sum and the carry? Well, we can just do data flow modeling, for example. Most of what we're going to do in this section is mostly structural, so that I can show you the different Verilog techniques. So we can say that assign, I want the sum, and the sum is just the XOR of X and Y, and that's it. Well, the operator for XOR is this little caret symbol. And similarly, I can say, well, the carry is just the and this is basically what we do of X and Y. And now we have the half adder, and that's it. Okay, so we built the half adder. What next? Well, if you take a look at this process in here, the half adder only takes a couple of bits in, a couple of bits in. I won't be able to add the carry in, so I need to add a third input. And the name half is not random, actually. And as it turns out, what we need is what we call a full adder. And what the full adder does, it will take a couple of bits in here and a carry in, and will do the same exact operation. It'll give me a sum and a carry out for the next step. And this is implemented in here. And I said the name is not in vain because you need a couple of half adder to compile or to build a complete full adder. Okay, so and the way you do it is by taking a look at this diagram. These two diagrams are exactly equivalent. This is one half adder and this is another half adder in here. It's just I'm showing you the different gates. So you can go ahead to Verilog and just implement it this way by taking the X and the Y and taking the XOR and so forth. But what I will do is I'll just re-emphasize the process of instantiation. And the reason why is because we already have built half an adder. I have a module that I can use and reutilize. All I have to do is just instantiate a couple of instances of this half adder and connect them with a little bit of an OR in here. So what I'm going to do right now is I'm going to build another module. I'm going to call it the full adder, and specifically that full adder, if you take a look at it from a black box perspective, it will take a few inputs. It'll take a carry, it'll take a carry in and an X and a Y. All of them are a single bit. It'll give me the sum of these 3 bits, and it'll give me a carry out that I can take to the next step. These little I subscripts in here and here, it's just telling me it's actually here because we're going to be using these full adders to implement the whole adders, like the two binary adders later. And I would represent the stage. Well, this is the first stage, this is the third stage, and so forth. Okay, so let's go to Vivado and write some code to implement that full adder. Okay, so I opened a new module, I called it full adder, and all I'm going to do is just utilize that half adder that you see at the bottom in here in it. So how do we go about it? Here. So as usual, I usually start by specifying what my inputs and outputs. Sometimes I do go back to these inputs and outputs after I write my code and I figure out that I missed one. But generally speaking, I look at this box that you see in here and I say, well, okay, I have 3 inputs and 2 outputs. So let me write these. So I have an input here, I have the X, I have the Y, and I have the C in, okay, or the carry in. Okay, and I also have an output, and there are specifically a couple of them. I have S and I have C out, okay? So these are my inputs and outputs. Now what do? Well, I have to instantiate a couple of these half adders, okay? Of course, I do not have to copy and paste that half adder code. I already have it. All I have to do is just create an instance of it, which we call instantiation. So how do we do this? Well, I will say, okay, so let's say half adder, okay? And then I'm gonna call it, for example, half adder 0. You have to give it a name, okay? And then I usually do this, and I will use name port connection, and that's the simplest. And what I usually do is I look at the half adder code in here and I say, okay, what type of inputs do I have? I have the X, I have the Y, and I have the C, and I have the S. You can of course connect them right away, but I usually write all of them and then go say, okay, what am I connecting to the X? Let me take a look at my diagram in here, and let's say that this is my half adder 0 is actually this one in here. Okay, so what am I connecting to it? Well, I'm connecting the X and the Y coming from the external. So I'm gonna say X here, and of course I'm gonna use Y. Okay, and then what am I connecting for C? Well, the C in here, let's call this as C1. So I'm gonna just use a different color so you can see it. I'm gonna call this C1. Okay, so I'm gonna say C1, and of course, well, not of course, you don't have to say the type of variable, like since it's a 1-bit thing, you can say that it's a wire of type C, or its name is 1, or C1. You don't have to do it again if it's 1, but if it's vectored, then you have multiple bits, or bus, or like it's a bus. That's what I mean by vectored. You have to specify it, but as a C1, you can just write it. But generally speaking, what I do is I write it so that it's more robust. My code is more robust and more correct. Okay, and then I'm gonna do in here and I say, well, this one is also giving me, I'm just gonna call it S1. Okay, I'm just gonna say S1, and I go usually here and I say, okay, let me do this S1. All right, so I instantiated my first half adder. So how do I instantiate the other one? Well, again, I don't have to copy my code. All I have to do is just say half adder, and this time I'm going to call it half adder 1. I usually do this here, and I say, okay, name port connection, so that I don't make any mistake. Name port connection is probably the most verbose version of it, or the most verbose types of connection, but it's really, it just reduces my errors usually. So I have my X and Y. What are my X? Well, let's take a look in here. If this is my H1, what am I connecting to it? I'm connecting the carry in, and I'm connecting dot someone, okay? So I'm gonna connect the carry in, and I will also connect the S1. Great. So how about the sum, the external one? It's actually the external sum, so I can, what did I call it? I called it S, so I'm just gonna connect S to it. Okay, and what about my carry out? Well, the carry out in here is also, I still need an OR gate in here, so I'm just gonna call it C2. Okay, so I'm gonna connect it to C2, and of course I'm gonna go back in here and I say I need C2, and that's it. So, well, not quite yet. We still have to do that. So I'm done with the half adder 0 and 1. All I have to do is just now is figure out the complete carry out, and which is just an OR between the two. And we can do this here, that way here, for example, you can say assign, okay, and then C out equals either C1 or C2. And that's pretty much it. And now my full adder is implemented. The whole circuit here is implemented, and you can test it on your board if you choose to. Before moving on to implementing the full binary adder that will perform this particular operation, I just want to re-emphasize what we did. What we did in here is we just created a full adder that takes 3 inputs, maybe a carry in and a couple of bits, and generates an output and maybe a carry out. Okay. This isn't the only way you can do a full adder. This is just one way. For example, if you go ahead and just write the truth table, for example, a carry in and an X and a Y, you can definitely generate the truth table similar to that, and you can just use K-maps and reduce it, and you have a couple of functions in here and you can implement it. This is exactly the same full adder, it's just implemented a little bit differently. However, in this particular implementation, I have a couple of things in here. So first, I'm not using any half adders, so I will not be able to show you any way to instantiate half adders or instantiate modules in Verilog. So where's the fun in that? I just wanted to show you the basic concept of a hierarchical design again in Verilog. And the other thing, which is historic, is here we're using this particular gate and this particular gate. And if you pay closer attention to it, it's actually a 3 input gates, each one of them. Or what we call, it's a fan in of 3. There's a fan in of how many inputs a gate has, and there's also a fan out how many outputs can you draw from it. Okay, and usually a fan in, historically speaking, it was problematic, like to have 3 or 4 or 5 or 50. In Verilog, I mean, you can definitely implement it, like you can do it. But anyway, what I just wanted to say is there isn't a single way to design something, and there isn't a single way to write code to describe the same thing, okay? So I just wanted to say that before moving on. Okay, so now we have the full adders. Let's move on to building a circuit that will actually add a couple of numbers, not only a few bits. So how do we go about that? Well, there's many ways to do it. I'll just cover what we call a ripple carry adder or an RCA. Okay, so let me explain to you what we're doing here. Of course, if you take a look at this diagram in here, what I have is 4-bit adders. So I need four of these full adders that we just created to perform the addition. And that's exactly what you see in here. And again, we're going to instantiate 4 instances of the same full adder we just developed. It's one here, one here, one here, one here. And what is it doing? Well, let's take a look. So we have, I'm just going to highlight it. I have X0 and Y0, and these are the 2 numbers in here. And I have a carry in. Well, the carry in at the beginning, it's actually 0 because I'm not using that carry in, okay? What does it generate? Well, it will generate that little 0 in here, and that will be the sum, and that's the first full adder. Okay, and not only this, it will generate that little one here, which is the carry out. What do I do with this carry out? I connect it as the carry in for the second full adder in here. So, okay, what about this second full adder? Well, this full adder will take that one in here. I'm just going to highlight it over. It'll take these and that, and which is Y and X in here, and it'll give me a sum and another carry, which is a sum and another carry, and so forth. And you can do this for as many bits as you want. And of course, at the very end, you will have that carry out in here, which is this little one in here. Okay, and that's the carry out, which is here. It's the same thing. Okay. All right, so let's go to Vivado and implement this and see how we can write code to describe this particular circuit. But before I jump into the implementation, I just want to emphasize, why do I call it ripple carry adder? And as it turns out, there isn't a single way to add a couple of numbers. There's a bunch of ways to design what we call binary numbers or multi-bit binary adders or multi-bit adders. This is a ripple carry because the carry, you put a carry in, it goes to this carry, and then when this carry is completed, like this full adder will be able to compute its own carry, and this full adder will be able to compute this carry and this adder. So if you take a look at it, the carry is actually just rippling between the full adders, and that's what we call the ripple carry. It might not be the best or optimum design, but it certainly is very easy to understand, and it's extremely straightforward to implement. Okay, and that's why we're having it here. There's another one that you probably have to look up, or you probably heard of it. Look it up. It's called a carry look ahead adder that does not have this here, and it's just a little bit faster. So we're going to be talking about timing later, but the timing in here is not as good because in order for you to get a full signal, you're going to have to wait for the signal to ripple through all the signal in here, or through all the different modules in here. But anyway, timing is for a different day. Let's just go to Vivado and talk about it. Or talk about the implementation. Okay, so I went ahead and I created another module now. I called it RCA, it stands for Ripple Carry Adder, and underscore 4-bit, because we're going to be implementing something a little bit different so that we can distinguish between them. Okay, again, we're gonna have to take a look at my ripple carry adder in here, and let me just surround it with a box so that I know what I need. Okay, I'll surround it with a box so I know which one is my inputs, which one is my output. And frankly speaking, I need to say input x1, x2, x3, and so forth, as you see in here. Probably I have to start by x0 as well. Okay, you can definitely do that. Okay, but what I'm going to do is, instead of just specifying all these signals as 1, 1, 1, x1, and x0, and x, since they all share similar names, I'm just going to use the vectored signals or buses. Okay, vectored stands for like multi-bit signals or buses. So I think the official term is vectored. Okay, so I'm going to do that, and the way you do it is by you open square brackets in here, and within the square bracket you tell it how many do you need. Specifically, you tell it the indices you want. So I wanted to go from 0 all the way to 3, and specifically I'm saying the least significant bit has to be 0 and the most significant bit has to be 3. It certainly isn't the only way you can specify that x in here. So let me just explain what I mean by this particular symbol. I will cover it here. Okay, so in here what we have is we have x0, and I said it goes from 3 to 0, and this is the convention usually we use it, and this tells me that the least significant bit is 0 and then followed by x1 and followed by x2 and then followed by x3. Okay, but if you wrote that code a little bit differently and you wrote it, for example, 0 in here and 3 in here, what you're telling me is the least significant bit will be x3, and then here will be x2, and then here will be x1, and this one will be x0. Both of them are correct in Verilog. It's not different. If you're writing your code, I recommend that you stick to this particular that's a convention that you use 0 as the least significant bit, which for obvious reasons it makes sense. Okay, so I usually write it this way so that I don't confuse myself. Okay, all right, so we did this here. Now I have my x as vectored, and I also can actually show you y as a vectored signal. And of course I have another input in here, which is, I believe, the carry n, and I will just call it c underscore n. And then of course I have the output, and the output is also, I mean, I can do S0, S1, S2, or I can just use it as a vectored, and I'll do the same exact convention, 0 to 3, these are 4 bits. Okay, and I have another output, which is just the carry out, which is this little one here. Okay, all right, so now I'm done with my inputs and outputs. Let me just go on. What do I do? Well, I need to actually instantiate 4 of these full adders and just connect them. And if you take a look at the circuit, there's nothing else but 4 full adders connected together. So let's do that. What I will do is I'll just do something like a template in here. I'm just gonna say, okay, I need a full adder in here. I'm just gonna call it FA0. We're gonna do 0, 1, 2, and 3. I'll open these brackets in here, and I'll do this, and then here, and I'm gonna say, well, I have an input, it's called an X, and I have an output in here, and I call it, or another input called Y, and I have a carry in, which is C, and I have, or the carry out, sorry. Let me just see, it's a full adder, not the half adder. Okay, so while I was reading from here, what I need to do is I need to read from this one. Okay, and that's why I usually open them right next to each other so that I know. Okay, so I have the half adder and the full adder in here. Okay, so let's take a look at that. So I have the X and the Y, and then I have the carry in, and of course I'll have to have the sum and the carry out. Okay, so this is the sum and this is the carry out. Okay, and these are actually all 4 full adders have to have the same exact template. So what I'm going to do is I'm just going to copy it, and I'm going to say, okay, here's another full adder, and here's another full adder, and here's another full adder. I believe I put 4 of them already. Okay, so that's fine. Frankly speaking, I don't need this now. I can call it full adder 0, full adder 1, and then this one is full adder 2. Let me just see, 0, 1, 2, and 3 in here. Okay, all I have to do now is connect the signals. So let me show you. So I'm gonna call my full adder 0 this one, this is 1, this is 2, and this is 3. Okay, what do I have to connect to full adder 0? Well, the X will have the X0, and then the Y will have Y0 connected to it. What about the carry in? Well, the carry in here is actually that little one here. And if you think about it, I don't really need a carry in for this particular operation. It's 0. So, but what I did is I exposed it to the outside world because maybe I want to replicate this ripple carry adder a couple of times so I have an 8-bit adder later if I wanted to. So all I have to do is just take that carry in from the outside world in here and just connect it to the very first one. Okay, what about the sum? I'm just going to call it S0 in here. Okay, what about the carry out? This is the S0 in here. Well, here's what we can do. we can just create C1, C2, C3 here. I don't have them, so I'll have to specify them. I can specify them as C1, C2, C3, but a better way to do it, generally speaking, is to define them as a vector here. And now, because I'm going to use it as a vector, you have to do that. It's a wire 3 to 1, okay? And you see what I did with the least significant bit? I didn't have to call it 0 like I did in here. I said I needed from C1, C2, C3, and that's it. I don't need the C out in here, so I can just go from 1 to 3. I don't have to start from 0. The least significant bit would be 1. And here, what I can do is I can say C1 is my output in here. Okay, the same goes with the second full adder in here. It's probably straightforward. So I posted the code. I recommend that you just take a look at it and read it. I'm just going to pause here, fill them out, and continue later so that I don't waste your time. And I'm done here. So what should I do next? You should take a look in here. My code is done. I connected everything as supposed to be. And of course, the last one, I connected the C output to the outside world, C out. And that's pretty much it. Before I move on, I just want to show you what has happened in here in terms of sources. So I'm just going to save this little guy in here, and I'm just going to show you here. I have a bunch of files in here. Don't worry about it. I just basically prepared it ahead of time. But the one I'm interested in is this one here, the one that is highlighted. I'm just going to make it as my top file. And of course, you can take it, implement it in your board. You have to add a constraint file and whatnot. But I just want to show you the concept of hierarchical design. What I have is I have a 4-bit ripple carry adder. It has 4 full adders in it, and each full adder will have a couple of half adders in it. So you see how convenient it is to do instantiation. All I have to do is just create one file for half adder, one file for full adder, and one file for RCA. And I just was able to actually just do all these hierarchies to implement a complete 4-bit adder. Before I move on, I just want to tell you that what I really do is, before I move on to my bigger code or bigger examples, I usually run some tests just to make sure that my code runs well. I mean, I wrote a half adder, a full adder, a ripple carry adder. And before I just continue, I have to test it to make sure that everything is fine. And what I'm showing you here is a simulation source or a test bench in here, which we're going to be talking about it later in this module. But what I care about for now is reading that test bench or reading the output from that test bench. And what I have in here is I'm showing you some results. I have generated like an X and a Y, and I generated the carry in, and I'm seeing the sum and the carry out. So let me show you what do I mean by that. Like I can stop anywhere I want, and this tells me if your X is 14 and if your Y is 10, you will get an answer, and the carry in of course is 0 in here. That's what you see, 14 and 10 and 0. You'll get an answer that is an 8. Well, does that make sense? Let's think about it. 14 plus 10 is 24. Well, what did we say in here? Well, let's think about it. Let's take a look at the binary numbers one more time. And the binary numbers, actually, if you look at it, I'm adding exactly that. I'm adding that 14, and I'm adding the 10 to it, and I'm supposed to get a 24. But what I'm getting is an 8. How am I getting an 8? Well, an 8 because these 4 bits represent an 8, and I have a carry out. And if you think about it, that's 8 plus 16, which is 24. So that's good. Let's test it with a couple other numbers. I generated this number here, which is 7 and 3. These are all in decimals, the numbers I'm showing you. They're actually unsigned decimals. So 7 plus 3 is technically 10, and the carry out is 0. Good. How about in here? What I'm having is 7 and 3, and what I did is I raised the carry in. So 7, 3 plus 1, it's technically 11, and that's what I'm getting, and the carry out is 0. So my code is working for these 4-bit adder. So we're done writing code for a 4-bit adder, and as a final thought, I just want to tell you that you might find this symbol or see this symbol in different locations, like on the internet or like in certain books, and this symbol generally represents an adder, and it could be an n-bit adder. In this case, I'm showing you a 4-bit adder. It takes an input, and this tells me that the input is X is 4-bit, the input Y is 4-bit, and the sum is also 4-bit, and it also takes a carry in and a carry out, and I'll be utilizing this symbol throughout the course.